everybody, and welcome to today's webinar. My name is Emily Sprenger. I'm an academic trainer in the Center for Teaching and Learning, and I'm thrilled to have Rachel Broom with us here today. She's one of our academic coaches, and today will be our very first CTL stats webinar. So we are going to learn from this process from you as well too, and maybe how we can better guide some stats webinars in the future as well too. But for today, we're getting down to the basics, explore basic stats concepts. Couple of brief reminders, this is being recorded. There was, for those of you that registered by Thursday of last week, there was a guide that was sent via email to you. I will actually pull the report and send the guide to everybody that's in attendance today as well too, just for you to refer back to. And if you have questions, please post all of your questions in the Q&A, or you can also post them in the chat. If you do post them in the chat, please make sure, if you want everybody to see your comment or your questions, so maybe we don't have repeat comments and questions, make sure you select the all panelists and attendees in the drop-down function of the chat. And then if we need to have you expand on your question and maybe it's too difficult to type, if you raise your hand in the participant section, I will allow you to speak and you can unmute yourself. So without further ado, I'm going to pass it over to our academic coach, Rachel.
Hi, everybody. I'm super excited to be here. If you've been in the Academic Success Center, you've probably encountered me in chat or maybe even attended the group session that I host. So I really felt like this is kind of an area that we've needed some support in. And Emily was also like, we really need to get some stats in here. So this, as she indicated, this is kind of like the baby. So we are seeing how this goes. There's so many stats concepts. I wanted to keep it focused. So as you guys ask questions and things like that, it's going to help us see, okay, is there a need to have another webinar from here to kind of build on these concepts or expand on a certain area? So please give us your feedback, ask questions, because those questions are going to help us know how to better help you in the future. So we are going to talk about some basic stats concepts. As she indicated, for anybody that was registered, hopefully you have had a chance to download and check out the handout that I created. So I want this to be interactive. And since this is a webinar, it's hard to kind of stop every few seconds and have questions and things like that. So I wanted you to have that handout to let you know what we're going to cover, give you an idea of what you already know about some of these concepts, and give you a better idea of, oh, well, I'm not really sure about this. I need to make sure I pay attention here. So as she said, go ahead, pop questions as we go into the Q&A or into chat, and we will tackle those when we get to them. So we are going to talk about measures of central tendency and dispersion. If you're not familiar with those stats terms, you might be more familiar with things like mean, median, mode, range, standard deviation, things like that. We're also going to talk about the standard normal distribution. And this, at least in all of my stats courses, this was kind of like the prerequisite to learning about hypothesis testing and statistical tests in general. You always start with the normal distribution. So we're going to talk a little bit about that and start to tie that into those hypothesis testing concepts that are going to apply to every hypothesis test that you do. So we have our measures of central tendency, central meaning the middle. Now, what the middle looks like is going to depend on which of these measures you're using. The mean, I'll start with. This is probably one that you're very familiar with. You've probably heard it a lot. And a lot of times when we talk about things, we always talk about the average. So even if mean's kind of like, well, I think I know what that is, you probably know what an average is. So mean is a very popular measure of central tendency. And we use it when we have continuous data. If you haven't been to my What's a Variable session, you might be wondering, well, what's continuous? Fancy way of saying numbers. We compute a mean when we have numbers, numerical data. We can compute a mean for things like age, height, weight, income if we have your exact income. GPA is a measure of averages, right? So we can compute mean whenever we have numbers that we can use to compute that. I have a note here that says that it's best with data that's normally distributed. We're going to talk about what that means. But this kind of hints to the fact that while we do use the mean most of the time when it comes to numbers, there might be some times when we don't want to use this. And when it's not normally distributed, what that means is it's skewed. And again, we're going to talk about what this means. There we go. But if we have data that has a hill on one side or the other instead of in the middle, then we wouldn't want to use the mean because the mean is going to be somewhere over here, not very representative of that data. So if we're going for that central tendency, we want it to be most representative. And in these cases, the mean just is not very representative. So let's talk about the median. This is what we would use if we had that skewed data. The median is when you put all the numbers in order and then you mark off one from each end until you get to the middle. The median is literally the middle of the list. So we're not averaging it, we're just finding the exact middle. That's our median. This works well when we have skewed data because it doesn't get pulled down to the end like the mean does, because those higher values don't change the position of the median. We can also use this for ordinal data. Again, if you're not familiar with those levels of measurement, you might be wondering what ordinal means. Just think of it like rankings, something that we can put in a specific order. So this might be something like if you're running a race, you can come in first, second, third, fourth. Those have an order. So we can find the middle of that list of orders. And then our last measure of central tendency is the mode. And this one, I would say, is not really a measure of middle. In a normal distribution, it would be, but the mode is actually the most occurring outcome. This works really well when we have categorical data, so not numbers. This might be something like gender, race, or ethnicity groups. This could even be like grade levels in school, freshman, sophomore, junior, senior, that kind of thing, where we have groups and we could report the group that had the highest frequency. That would be the mode. This works really well, like I said, nominal data. We can also use it for ordinal data, things like that. So these are the three measures of central tendency. When you're reporting these statistics, you want to make sure that you're choosing the appropriate one, usually first based on level of measurement. You don't want to report a mean, for example, if you have categorical data. And I'll use the example of gender. And I'm not going to be PC with this. I'm just going to be very basic to help break this down. So if we go with gender in its most basic form of male and female, if we assigned numbers, because again, to do mean, I need numbers. So if we said 1 is male, 2 is female, and then I compute the mean. So I add up all of my 1s and 2s, divide by how many people I have in my data set, I'm going to end up with some number between 1 and 2. It might be something like 1.37. And then we interpret that. It's like, okay, so the average gender is 1.37. Does that make sense? To me, it doesn't. Now, if you said the average age was 23, I get that. That makes sense. On average, people 23 years old. But when you say the gender, the average gender was 1.37. On average, people were more male than female. Doesn't make sense when we think of it in simple terms. So we need to choose carefully which of these measures of central tendency we're choosing for each of our variables. So when you're running those descriptive statistics, choose which measure you're reporting. Don't just put a table with all of the values, only the ones that are most important. Just like we wouldn't want a mode for continuous data. If we had 100 people in a room and we collected the ages of these 100 people, we would be hard-pressed to find one age that had a very large number of people on that age. We're going to have lots of very different numbers. So it would be hard to find a mode, or we might have multiple modes, and even then it might just be like 3 people out of 100. So it's not really representative having a mode for a continuous variable. So this ties into dispersion. And dispersion is just talking about the variability in the data set. So while it's great to know what the central tendency is, Also, knowing how much variability there is in that data set helps to give an idea about the sample that you're dealing with. So there's three common ones that are used. The range and interquartile range are very similar. I think the interquartile range is more appropriate when you have some really unusual high and low values that kind of offset what's most representative, whereas the interquartile range is going to be more representative for data sets that have those weird, unusual values. Standard deviation, again, is probably one you've heard of and are a little more familiar with because you often see it paired with the mean, and it works really well for that continuous data and for those normally distributed distributions that we're used to working with. So the range is simply the difference between the highest value in your data set and the lowest value in your data set. Super simple, just identify high and low, subtract the two, and that's your range. Interquartile range is just as simple, still a range, so you're still subtracting high and low. However, instead of using the highest and the lowest values in your data set, you want to use the first and the third quartile. Now, you're probably like, well, I don't know what those are. Simple. A quartile, if you think of quarter is like 25% of a dollar, right? Or 25 cents. Same thing. A quartile marks those 25% marks in your data set. So the first quartile is the first 25% of your data. The third quartile is the last 25% or has 75% below it. So you would find that 75th percentile and that 25th percentile and subtract those values to find the interquartile range. Again, we want to use this when we only have numbers, and we want to use it with data that's probably not normally distributed. Again, not that nice bell curve shape that we're going to talk about here in a minute. And then, as I mentioned, with standard deviation, this works really well when we have very pretty normally distributed data. And the standard deviation is an average. It's kind of like a mean. And what it is the average distance of each point in your data set from the mean. And I think that this one's probably one of the easiest to interpret as you're talking about variability. If there's a lot of variability, then your standard deviation is going to be quite large. So part of that's going to depend on the scale that you're working with for your values. So there's no set number for what's a good or a normal standard deviation. Just know that in relation to the scale that you're working with, smaller standard deviations means that your data doesn't vary very much. Everybody had very similar scores, whereas a larger standard deviation indicates that there was a lot more variability in those scores. So I wanted to talk about the roles of level of measurement. So I touched on this when I was talking about those measures of central tendency and trying to choose the appropriate ones based on the level of measurement. So we're going to talk about these levels of measurement just a little bit. So as I mentioned, categorical, continuous, that's usually where I start. And on a very basic level, I just think categorical is words. So if I have words or groups, it's probably a categorical level of measurement. If I have numbers, it's probably continuous. And then from there, I can break it down into nominal and ordinal. We do have some examples of these levels of measurement on our website. And you can also attend the What's a Variable group session that's held on Thursdays at 11 a.m. Arizona time and learn more about these levels of measurement. And we do a lot of practicing, making sure that you feel comfortable identifying these levels of measurement as well. So if you're not familiar, I definitely encourage you to join that group session to learn a little more about these types of levels of measurement. So I want to switch into the standard normal distribution. So I have a picture of this curve over here, and you'll notice that it has z-score down here at the bottom. The standard normal curve is also referred to as the z distribution. So if you work with z-scores, you're working with the standard normal distribution. And you can see that it has a nice symmetrical shape, meaning that if we fold it in half on the mean, both sides are mirror images of each other. Or when we're working with real data, they're roughly mirror images, because in the real world, our data is never going to look this pretty. So for normally distributed, we're looking for approximately normally distributed. So a lot of continuous variables in the population, thinking things like age, height, IQ, things like that, a lot of those variables already form a very normal distribution naturally, which is great. So we can do a lot of testing on those variables using this curve. Some important things to know about this specific distribution. It has a given mean and standard deviation, hence the reason that it's standard normal. It's a standardized distribution. So it has a mean of 0 and a standard deviation of 1. We could use this standardized scale to allow us to compare two data from two different scales. And I'll give an example. So if you wanted to compare, for example, performance on the SAT to performance on the GRE, obviously you can't just look at the score and be like, well, I got a 1300 on this one and a 700 on that one, so I obviously did better on 1300. It all depends on the scales. What's good on the SAT? What's good on the GRE? And I know nothing about what those actual scores are. I made those numbers up. I don't even know if you can get a 700 on the GRE. But you can see those are measured on two different scales. So it would be really hard to just look at your score and know if you did well or did poorly. So you could convert both of those scores to this standardized distribution and then compare them. So when you do the conversion, you're going to get a z-score for each one. And the z-score that is higher, so up near the positive 1, 2, 3, something farther that way, means that you did better than one that's closer to the mean or on the negative side. So you can make a direct comparison of the performance of two different scores that have two different scales by standardizing using this standard normal distribution. So this ties us into the probability testing. So one of the easiest ways, I think, to introduce this is with the empirical rule. And this is talking about the percentage of data that falls at given points on this distribution. And here we have the mean in the middle. And in a normal distribution, the mean is exactly in the middle. So half of the data is above the mean, half of the data is below the mean. This is really helpful when we're computing probabilities. So if you're trying to find the probability of something happening, or if you want to find the percentage of people that fall above or below a certain point, or if you want to find the score associated with a given percentile, we can use all of these interchangeably on this normal distribution because those percentages are standardized. So the empirical rule follows this 68, 95, 99.7 rule. And what that means is this middle percentage. So from the low end of the purple section to the higher end of the purple section, this represents one standard deviation from the mean. That means I went one standard deviation below the mean, and I went one standard deviation above the mean. And that's this purple section. That would encompass 68% of people on that measure. If I wanted to bump that out to 2 standard deviations, then I'm now including the green. So if I went, this is 1 standard deviation below. If I go 1 more standard deviation below, I'm now 2 below. And then same going the other way. If I go up 1 standard deviation, up 1 more standard deviation, I'm 2 above, 2 below. So I'm 2 standard deviations from the mean. And I now am including 95% of the people on this distribution. And we could do it one more time and go out 3 standard deviations above and below. And we now encompass 99.7% of people. So this is where this idea of what's statistically significant. And this is where hypothesis testing starts to come into play. So using these general ideas, basically, if we think about it, 95% is normal. most people are going to fall within that range. So that's roughly 2 standard deviations above and below the mean. That's 95% of people. So if you think of it this way, if you collect a sample of people from a given population and you compute a mean for that sample, that mean should represent your population. And so when we get into hypothesis testing, we compute this mean and we're going to compare it back to our population, and we're going to determine, did this sample really come from the population? Is the sample representative of the population? Statistics are very open to interpretation. We understand in statistics that nothing's ever black and white. And while not probable, it is possible that I do in fact pull a sample of people from a population that do represent that population, but I just happen to pick all those unusual people. And when I run my data on this sample, it doesn't actually represent the population, even though it should. So that's why we have, I call it wiggle room. So when we're thinking about those differences between our sample and our population, or even two samples, we're looking at not just are the numbers different. So if I computed a mean for one group and that mean was 30, and I computed the mean for another group and it was 37, I can look at those two numbers and say, well, yeah, the second group was definitely higher. They had 37. But statistically, I don't know that that 7-point difference is actually meaningful, because if I look at this normal distribution, well, 68% of people, they're not going to be right there at the mean. I don't have everybody at 30 or 37 points. There's flexibility, and I call that my wiggle room. So when you're looking at those statistics, while this sample's mean was 30, there's wiggle room around that. Not everybody had a 30. They just averaged to 30. So I need to know if that flexibility still includes my groups. So is that 7-point difference within that range of what I would consider normal? So that 2 standard deviations, this 95%, is that including both of my groups? If it does, then even though numerically 30 and 37 are different, I would be able to say that they're the same. They don't have to be exactly the same. They're both normal for a given distribution. So they're not different. If, however, they fall outside, so they're not included in that 95% range, I can now say, well, they are different. They're different enough that they're not both normal. So I can conclude that my groups are actually different. That 7-point difference was different enough to be significantly different. I wouldn't expect to get that big of a difference if these groups came from the same population. Hopefully that makes sense. All right, so I want to look at some of the questions that have been going on.
Yes, a couple of questions, some stuff in the chat. Is there any data any data transformation that can transform a real world data into normally distributed?
There are, typically, if your data is not normally distributed, you don't want to force it to be. But there are transformations that can be done that's like way advanced statistics. So I don't want to elaborate on it here. But if you are dealing with a scenario like that and you want to explore options, then I would definitely encourage you to reach out to the Academic Success Center and schedule an individual session. And a stats coach could go over those options with you. But normally, if your data is not normally distributed, you would just opt for what we call non-parametric tests. So you wouldn't use a test that requires your data to be normally distributed. You would use a different test that is open to data being non-normally distributed.
Thank you for that, Rachel. And just a heads up, I know I popped it in the chat, but I did resend the document that she plans to go over. So I know some of you already received it and some of you didn't. So just so you're aware, it's in your email box as long as you put the correct email for registration. One more question in the chat. This is from Christopher. Greetings. Does the empirical rule change if you are only looking at one side of the mean?
That's a good question. So the rule doesn't change. But when you're talking about like hypothesis testing, for example, so if I'm looking at this 95%, in the empirical rule, that's 95% in the middle, which means that there's 5% outside of that, but that 5% is split in both tails as opposed to being in just one tail. So if you're only doing what we would call like a one-tailed test, and you're only like if you predict that one group would have a lower value than the other, you would only be looking at the left tail. And if you wanted to say, again, going with that 5% cutoff of being abnormal, then you would want all 5 of that percent in the tail. So in that case, you would not be using the empirical rule for this. You would want to go, let's see if I can make this go back here. There we go. You would want to go back to like the normal distribution and actually look at that 5% or find the z-score that's associated with 5% in that tail, as opposed to using that empirical rule.
Thank you, Rachel. Can I ask one more question before we move on?
Yeah.
What about data that falls out of the 3SD? Do we consider it?
So anything outside of the 3 standard deviations is extremely unusual. And depending on, like if you're using SPSS, they use for their outliers, I believe it's like the 1.5 from the quartile as the outlier algorithm. But you might be dealing with like what we would call like outliers. So very unusual values that are going to influence the results of your test. So something that's more than 3 standard deviations above or below the mean is extremely unusual. So again, if we look at this empirical rule, this idea that if it's normally distributed at 3 standard deviations, I've included 99.7% of my population. So anything outside of that is unusual, but not impossible, right? That means that there's still 0.3% of people that are part of the population that just have unusual values that are still part of that population. And so that's something to take into consideration. And again, why in statistics we understand that everything's kind of a gray area, everything's open for interpretation. So when you're doing that hypothesis testing, you're not accepting the alternative. You're not proving that something is correct. All you're doing is you found data that suggests this is correct or suggests that this isn't possible or things like that. It's just suggesting, because there's always a chance that your data is wrong, that your data does not represent the reality of the population.
And there are a few more questions in the Q&A.
Yeah.
But I'm wondering if the interest in time, if we should move forward. It's up to you. You tell me.
I was going to say, let me see. So I would say I've already kind of touched on this, and I think this is the last part that I was going to do. So, great. I mean, I'm fine if we want to do questions.
Okay, great. Let's do a couple more questions then. So one more question in the Q&A. Can you talk about skewness and how we can deal with this type of distribution?
Sure. So here on the board, you can see this is a normal distribution. It has a peak in the middle and it tailors out into tails on both ends. And it does this uniformly, obviously, because this is perfect, but in the real world, it may not look exactly the same, but the general pattern is similar. In a skewed distribution, as I showed earlier, you're looking at something more like this, where the peak is off to one side, or you could have the peak on the other side and it tails off the other way. But skewed simply means that the peak is not in the middle or approximately in the middle. It's very much on one side or the other. There's a large accumulation of values on one end of the distribution and very few values on the other end of the distribution. So kind of like when I was talking about the outliers, sometimes this just means that you would not be able to use a statistical test that requires the data to be normally distributed. Simply for the fact that if you did, you might find significant results, but it's just because your data is significantly different from normal, and the test assumed it was normal. Or you could find non-significant results simply because your data wasn't normal and it needed to be in order for you to find that difference that you were looking for. So when you have skewed data, you kind of want to consider a few things like, is it skewed because there's some outliers? And if there's outliers, you may consider removing that data and then analyzing it without the outliers. Or you may consider other options for dealing with outliers. Sometimes we would just remove that value and input the mean instead of the outlier value, things like that. Again, there's options to explore there. But you could do some small things like that if it's only a couple of values that would help maybe make your distribution normal. But really, we don't want to change the data. So if you get skewed and you're like, well, I really needed it to be normal, you don't want to try to force the data to be normal. Because at that point, especially if you do a lot of tweaking, how much are you falsifying at this point just to make it normal? So there are tests and other things that can be used if the data is skewed. So you might want to explore some of those options to allow you to use your data as it is before exploring options to try to modify your data or remove some of those unusual values that would make your data more normal.
Thanks, Rachel. And I've seen a couple of people ask questions about this in the chat, and I've received some emails already. This is being recorded. We are going to post it in the CTL webinar LibGuides page. But a couple more questions, if that's all right.
Yeah.
Does the empirical rule change with the number of data points?
Nope, because it's based on the standard normal distribution. So the empirical rule will not change no matter how many points you have. However, if you have just a few points, so less than 30 is usually kind of a general idea. If you have fewer than 30 people in your sample, for example, you won't be using a standard normal distribution at that point. You may be using, so some of the examples that I have over here, like you may use a t distribution. Or if you're doing a different type of test like a chi-square, you may be using the chi-square distribution or the F distribution. So normal distributions are not the only distributions out there. So the empirical rule is specific to the normal distribution. And again, this is why I said, like, this is the baby. This is like the smallest introduction to statistics possible. But if I tried to put too much in, then this thing would go on forever. So I absolutely, I want to be able to elaborate on this in future webinars. We do also offer group sessions in the Academic Success Center that talk about some different types of statistical tests. So if you're doing like ANOVAs or correlations or regressions, things like that, we do have group sessions that focus on those specific analyses as well that might be helpful if you're at that point. So I would definitely encourage you to check those out and see what's already out there as well.
And I'm so glad you mentioned that, because there's two more questions in the Q&A, but one of the questions, and I feel like this is something that you and I talked about and having a need for webinars with stats. How much math background do we need for these classes?
I really think that depends. I know some students that have even come from statistics, like done statistics before, that have gotten into the courses and they're like, oh my gosh, I have no idea what I'm doing. Other students that have no statistical background at all come into it and it makes perfect sense. There's a lot of people, stats professionals and not, that argue that statistics is like learning a foreign language. There is a lot of terminology and concepts that go into statistics. And so sometimes you can look at it and just be overwhelmed with the jargon. And in my experience in the Academic Success Center, especially for students that aren't as familiar with statistics, sometimes the sheer number of resources each week feels overwhelming. And a lot of those resources are for people like me that are read write learners. If you don't know your learning style, I encourage you to find out, because it's going to flip your learning world upside down once you do. But they are, they're articles that are written out. And so for people that are more hands-on, for people that prefer hearing information to receive it, it can be hard to self-teach using the resources that are in your course. So I would absolutely encourage students that are in statistics courses, especially if you're new to statistics, jump into those materials early in your week to kind of get an idea like, am I doing okay with this material? And give yourself time to reach out for support. Um, I love the internet. I love YouTube. I love Google. I caution you to go Googling and YouTubing resources simply for the fact that if you're not familiar with the concepts and you're like, okay, well, I need to know something about t-tests, and you go find YouTube videos on how to do a t-test, there's like 3 or 4 different types of t-tests. And if you're watching a video on the wrong one, you're going to be like, well, I'm trying to do it and it's not working. And you're going to get more frustrated. And then you just spent hours finding that video. And then you get to somebody and it's like, oh, well, that's not what you're doing. And then you're like, oh my gosh, I just wasted all that time. Save yourself trouble. Come to the Academic Success Center. Let us help connect you to some resources or join one of our group sessions or an individual session just to make sure that you're getting the resources that are in line with what you're doing in your course. That way you're not wasting all of that precious time and getting stressed out and frustrated trying to navigate all the resources that you are taking time to locate because you're having a hard time understanding your course resources or understanding them. Reach out to your instructor and let your instructor know, hey, I'm feeling kind of overwhelmed with these resources. I'm having a hard time connecting the resources to the assignment. Communicate, reach out, let your supports know what help you're needing, and we will get you that help. And the earlier that you can do that in the week, the more time that you give yourself and the more stress you're going to save yourself from pushing it off to the end of the week.
I love that. I love that tip there. Thank you so much, Rachel. I do have a few more questions, but I want to check in with you to see if there's anything else that you wanted to cover.
Are the questions pertaining to things that we already talked about earlier?
There's some questions about outliers, and then a log, standardization, a like transformation. Do you want me to address those now, or should we?
So the transformation stuff, no, I will not go into that in this session because all of that's advanced. That's very advanced statistics stuff. That's nothing that you're going to learn in a basic statistics course. Okay. I know you don't cover it in statistics 1. I do believe that I have seen a couple students come in that are in maybe stats 2 or maybe just a different non-dis stats course. But I have seen, I believe, a couple students come in that are working with transformations in data, but for the most part, I don't think that most of the students are going to encounter scenarios where they need that. Not saying you might not need it once you reach your dissertation, but if you have questions on how to transform data in that way, so those log transformations or anything, schedule an individual session with the Academic Success Center so that you can work with a coach, because we don't have group sessions focused on those specific concepts. We don't have resources on our website that are for those specific concepts. So to get that support, I would definitely recommend just doing an individual session.
Okay. And then
outlier question. What was that one?
I think actually we're getting some questions in the chat if we can go over the worksheet just to make sure that we have enough time, because we do have just about 20 minutes left, and then we'll see if we can get back to these questions at the end.
Sure. Okay. So let me touch on this because I know this is on the worksheet as well. So when we're doing hypothesis testing, and I've touched on this where we're talking about that 5% that we're okay with. So we have what we call like a level of significance. This is also called alpha, and that's this Greek letter A. And this alpha value is also the chance of making a type 1 error. Type 1 error means that we determine that our sample says our results are significant, when in fact that population says, no, you shouldn't find a significant difference. Basically, this is a 5% chance that you take a pregnancy test, it says you're pregnant, but you're not really pregnant. That's what this is. So you want to keep that alpha, that chance, really small. You don't want to have a big chance of finding significant results that aren't actually correct. So this is why we keep this value very small. This is defining our critical region or our rejection region. And if you think of it as a rejection region, it'll help because when you're doing hypothesis testing, you're either rejecting the null hypothesis or you're failing to reject that null hypothesis. So if you think of this as a rejection region, if your p-value falls into this rejection region, you get to reject the null hypothesis. And it's always the null hypothesis. So in order for a p-value or an associated probability, you're going to see that on your assignment. That's what that's talking about. Associated probability just means the probability of your test, or in SPSS, it's SIG, S-I-G period. If for the results to be reject the null, it has to fall into this red region. In order for it to fall there, the probability or p-value must be smaller than your alpha. Alpha is this critical value when you're doing the p-value decision rule. So this critical value, alpha, would be, say, 0.05, which means that 5% of the distribution is in this red tail. So in order for my p-value to fall into this red region, that p-value must be smaller than 0.05. And if we think of it as percentage, this is 5%. In order to be in this range, the percentage above it must be smaller. So let me put something on the board. So like if in order for my p-value to be here, this area above the p-value, which is going to be that significance or that associated probability, it's going to tell me the percentage of data that's above the test statistic. That must be smaller than 5%. So this needs to be, say, 3% or 0.03 as my significance goes. If it's something greater than that, it's going to be over on this side, which means it's normal for my data set. It's not significantly different. And again, even if I have a value that falls into this rejection region, I didn't prove that my data was significantly different. My sample just suggests that it is. Because if my alpha is 0.05, there's a 5% chance that my data is wrong. So I didn't prove anything, I just supported a position. Now that's the p-value rule. So if the critical value is alpha and you're comparing a p-value to alpha, or that level of significance, we followed the p-value approach. I would argue that 95% of the work that you're going to do in your stats classes is going to use that approach because you're using SPSS to run your tests. So you're going to get that p-value from SPSS to compare to alpha. The traditional approach is using a critical value. So we could have, this is the test statistic that I have listed here. So instead of saying, okay, well, this is alpha as my critical value, you can look at the distribution and figure out which value would cut off 5% of the data or whatever you want your alpha to be. So that might be something like, well, a t of 2.37 would give me the percentage in the tail that I want. So then you're using the traditional approach. You would compute your test statistic t and compare that to 2.37. If it's greater than 2.37, it's in the rejection region. You could reject the null. If it's less than 2.37, it's going to be closer to the mean and you would fail to reject. This is not an approach you're going to be using in your courses very much because everything that you do for the most part is in SPSS. So as long as you know the p-value comparing to alpha approach, you should be good. I have chi-square and F on here. These do not use a normal distribution, so they would not actually look this way. Both of them actually have skewed distributions. So conceptually, rejecting the null and all of that stuff works the same. However, the shape of the distribution is different. So the balance isn't the same. All right. So I think that was all that I was going to talk about. Yep. So what other questions did we have before we wrap
Yes,
up?
we do have a couple more questions.
Perfect.
Statistically important results don't imply the causation, just that they haven't happened by chance, right?
That's a really great question. Actually, causation comes from your design. So, for example, the very famous phrase, correlation does not equal causation, which means if you are just measuring correlations, if you're just seeing if things are related, for example, you can't say that because you're a taller person, you have a higher IQ. Even though height and IQ are correlated, you can't say that one caused the other. Experimental designs are really the only ones that allow you to make a causal statement. You can only determine that one thing caused the other if you ran an experiment, which means that your groups were randomly assigned and you controlled all of the other variables, thus proving that any changes are a direct result of your experimental variable. So, no, statistical results do not mean that one thing caused the other. It simply means that the test you ran was significantly different than whatever the null is.
All right, thank you so much. Can you please, oh, excuse me, sorry, my microphone was here. Hopefully you could hear me okay.
Yeah.
Could you please re-explain p-value?
Sure. So the p-value is the probability of the test. So basically, like I'll use a t-test as an example. So when I run the t-test, what I'm looking for is a difference between groups. Usually I'm comparing two different groups. So for example, if I wanted to compare IQ based on gender, and so I had a group of males and I had a group of females, and I wanted to determine if IQ is significantly different based on which group you're in. And so I'm going to run the t-test. I'm going to obtain a test statistic value. It's going to be a t-score. And so the p-value would be the probability that I get that score if my null hypothesis is true. And in a t-test, my null hypothesis is that my groups are equal. There's no difference. My alternative might be that there's a difference. It could be that one is higher than the other. The alternative is what I think the data is going to show. So the p-value is the probability that I get my test statistic given that the null is true. So if my groups are the same, and they should have the same IQ, and again, when I say same, I mean not statistically different IQs, then what's the probability that I get my test statistic? So going with a small p-value, let's say it's that 0.03 that I was talking about. That means there's a 3% chance I would obtain my test statistic if those groups were actually the same. That's not a very big chance. If my groups are the same, there's only a 3% chance I would get what I got. That's a pretty good indicator that they're not the same, they're different. Versus if that p-value is a little larger. So maybe I get 0.13. So there's a 13% chance that I would obtain that test statistic given that my groups are equal. 13%, still not a lot, but in the realm of statistics, 0.055% is usually the highest that will go. So if I get 13%, I would say, well, I'm going to err on the safe side and just say that they're the same because it's kind of likely that I would get that difference. So the probability, that p-value, is associating that test statistic that you obtained and just saying, what's the chance that you would get that test statistic if your null hypothesis was true? If it's not very likely, then it's a stronger indicator that the alternative hypothesis would be true.
Thank you, Rachel. And I want to make sure I get to this question because it's one of the first ones in Q&A and it's the outlier question. And
okay.
Hopefully we'll have time for the others. Are outliers the ones outside of the 3 standard deviations?
So they absolutely will be. But again, it depends on what rule you're following in order to identify outliers. SPSS will automatically, if you run like the box and whisker plots, it'll automatically identify outliers. I believe that it follows the quartile rule. So if you take the third quartile times 1.5, anything above that would be a upper outlier, and then the first quartile times 1.5, anything below that would be a lower outlier. So not quite 3 standard deviations out. So it kind of depends on what approach you're using. I think a good rule of thumb when dealing with a normal distribution is to consider anything that's more than 2 standard deviations away from the mean to be unusual. Not necessarily an outlier, but unusual for your data set.
Thank you. And let's see. Sorry, guys, I have a little visitor over here who's trying to be really patient. Is the Pearson's R have any relation to the topic?
That is a correlation test. So Pearson, I guess it relates in the sense that it requires that your data is continuous and normally distributed. But other than that, that's not something that we talk about in here. We do have a correlation group session though, where you can learn about like testing the assumptions of the test, running the test in SPSS, interpreting the outputs, things like that. We also have some correlation resources on our website, and it kind of breaks down the Pearson and differentiates Pearson from Spearman and point by serial, things like that.
Thank you very much. And then while we have just a few more minutes, if anybody has a specific question about the worksheet that maybe you want Rachel to speak about a little bit more, please let me know. Oh, is there any way, this just popped up in the chat, is there any way you can review question 2 and question 4?
Yeah. Okay. So the statistics of the standard normal distribution, it has a mean of 0 and a standard deviation of 1. So that's with this normal distribution here. So you can see the mean is here in the middle and it's 0. So the mean of the standard deviation or standard normal distribution is 0. And then it has a standard deviation. So on average, as we move away from the mean, that standard deviation is 1. And this is going to be the same anytime you're dealing with the standard normal distribution or the Z distribution. It always has a mean of 0. It always has a standard deviation of 1. And then.
So that was question 2, correct?
Yep, that was question 2. And then number 4. So the mean of a normal distribution separates the upper blank percent of the data from the lower blank percent. So this is working off of, I guess, the empirical rule, but also just general conceptualization. Our mean of a normal distribution is always right in the middle. So it separates the upper 50% from the lower 50% because the mean is in the middle, and in normal distribution, we can fold it in half and they match.
And then if there's any other specific questions on the worksheet, please let us know. And let me see, I do have another one just while we wait to see if anybody else has any other questions on the worksheet.
Okay.
Is critical region found on both sides of the curve? And then is it related to SD in any way?
Not related to standard deviation, but it can be on both sides of the curve. So I do have in my what's a variable, I do have a picture of it. But that would be what we call a two-tailed test. So I talked about this when I gave my t-test example. When we're talking about testing a claim, we could be focused on only one tail. And what we call this one tail or a directional test. And you can think of it as your claim is predicting a specific direction. So if I think, for example, like females have a higher IQ than males, then I'm only focused on one tail because I only think it's going to be higher. I don't think it's going to be lower, so I can ignore that tail. Versus a two-tailed test or non-directional test, meaning I think that there's going to be a difference. I don't know who's going to be higher, but I think that they're going to be different. One is going to be higher than the other. I just don't know which one. In that case, I'm looking at both tails because I want to make sure that if there's a difference, I'm capturing it regardless of if it's higher or lower because I don't know where it's going to be. So yes, I could have a critical region that would fall into both tails. And in that case, what it's going to look like is one tail is just going to be irrelevant. So you're going to run your data, and if you get a test statistic that's positive, then it's going to be a upper tail. If you get a test statistic that's negative, again, for a normal distribution, then you're looking at the lower tail, and you would ignore the other tail.
I do have another question about the worksheet. If you
Yeah.
could, the answer to number 6, and then some people were asking if the answers will be posted by chance.
I can post the answers, yes.
So I can send that in a follow-up email to all the people that were registered?
Yes.
Okay, great. Yep. And then for now 6.
So number 6, so the critical value, which I identified as this point here. So this point, it cuts off the rejection region. So we would be looking at B, the value that identifies the cutoff for a particular level of significance. So this could be alpha, meaning that it cuts off that upper 5% or outside 5%. It could be my alpha, or it could be a test or a critical value for a given test statistic. So it could be the t-score that cuts off 5% or 1% or whatever chosen percentage I have for this rejection region. But the critical value is that cutoff. It has to exceed that cutoff or that critical value in order for me to find significance. If it does not exceed it, then it's not significant.
Thank you. I have a question about alpha. Is there a danger in making the alpha value too small?
Yes and no. The smaller your alpha, the harder it's going to be for you to find significance. So usually 0.05 is kind of like the maximum that will allow in statistical tests. Your p-value could absolutely be way smaller than that. But if you set your alpha, for example, to 0.01 or 1%, so you want a 1% chance of finding significant results when you shouldn't. So very, very small chance. That just makes it harder to obtain significant results. So in that case, you could run your test, and if you come up with a p-value of 0.04, which is still small, you would say, well, it wasn't small enough, so we failed to reject. Whereas another researcher may find that and say, hey, that's smaller than 0.05, so I get to reject the null. You found two different results with the exact same data, simply because your alpha, your cutoff, that threshold, was much smaller. So usually we use 0.05. When you might deviate from that would be if you're running multiple statistical tests on the same set of data. Every test has its own alpha. And so your overall study, you want the significance of your overall study to be around 0.05. So if you have multiple tests, then you might want to reduce the alpha of each individual test to keep that overall alpha under that 0.05 threshold. So there's not harm in having a small alpha. It just really makes it harder to find significance.
Thank you for that clarification. And then just because we started just a few minutes after, I'm going to see if we can do this last question before we wrap up.
Yeah.
Question, is this content covered in Stats 1 or 2 or both courses?
I honestly don't know. I haven't taken either of the courses.
It's okay. Fair.
I would almost argue, in my experience with students that have come into the Academic Success Center, I've honestly never seen them actually ask questions about any of this. However, I've gone over all of this with many of them because to me, this is foundational. And so I know that in previous meetings, we've talked about how some of the courses, while they don't have prerequisites, they do kind of have an assumption that you understand certain concepts coming into the course. And so I kind of feel like these are some of those concepts that it would be helpful to understand going into your course because it might help other things make sense if you understand the foundational stuff. So
And
I don't think that this stuff is actually covered in the courses, but I do think that at least in my education, these were foundational concepts building into the things that you're talking about in your courses.
and it could also vary by program as well
Yes.
too, right?
Yep.
So we're not each student is a part of a different program and a different specialization. So
They are.
but I want to first of all, so just so you know, Rachel, I don't know if you've been able to see the chat throughout your presentation, but so many people said thank you so much for taking the time to go over this, and it was very informative. And low stress is a word I saw in the chat
Yes.
when we're in conversation of stats. So that's great. We look forward to working together on the academic side and trying to find more opportunities to bring these types of webinars to our students. So your feedback
Absolutely.
is welcomed.
Yes. Yes. Like I said, I want to help connect. My goal is to help connect all the students to resources for the basics. We have
Absolutely.
tons of resources. And when I came into the Academic Success Center 2 years ago, our resources started with like ANOVA and t-tests, which for me, that wasn't like beginning of the year statistics. That was like end of the year statistics. So things that we got into after we covered lots of other things. And so over my last couple of years, helping students, seeing the questions that they had related to probability and statistics, I've been helping to develop a lot of resources for our website that focus on some of those building blocks to get us to t-tests and ANOVAs. So that's what I really wanted to focus on in this webinar, was some of those building blocks. And I would love to hear what other building blocks you would love to learn about through a webinar, and we can look at incorporating those into future webinars.
Absolutely. And feel free to reach out to me directly at espranger@ncu.edu if you need a direct link to this webinar. And then obviously use your resources that we have for you. Go to that ASC chat and start setting up some tutoring sessions. And I just want to thank my 4-year-old who's over here, who's waited patiently through the webinar, and thank all the participants and attendees today. And Rachel, thank you so much. We appreciate you.
Yep. Thank you everybody for coming. Emily, go give that 4-year-old some ice cream.
I know, right? Bye-bye.
Bye everybody.